You may ask me why I'm talking about n-grams when we have transformers, the technology of ChatGPT, and many architectures for transformers. They can create any kind of text. They can generate everything. And why I'm talking about n-grams, which is a very old thing. It is not new. So I will answer that we still need n-grams, and they are very important things for not only for theoretical purposes, but also for recent algorithms. Because you combine these language models with other problems in order to solve those tasks, NLP tasks or natural language understanding, even in semantic parsing, even in any task that you need in natural language processing, we can augment it with these ideas. So as you know, these are great scholars and great articles. Bert Score, and approximating, this is really good article in 2021, approximating probabilistic models as a weighted finite automata. So if I use Jurafsky's slides, then because they are very beautiful, so machine translation, in machine translation, you can. So the application of these n-grams is that you can understand what is the probability of high winds tonight is greater than large winds, and you can use it for spell correction. The difference is about 15 minutes from my house. What is the probability of about 15 minutes from to be greater than probability of about 15 minutes from? So this should be meaningful. Otherwise, if it is wrong. So it has many applications. For example, speech recognition. If we understand that, then we have better speech recognition models, and also for summarization, question answering, and etc. So what are n-grams? An n-gram is a sequence of n words. A 2-gram is a 2-word sequence, like please turn, your homework. These are two words. And we have also three grams. You can generalize it to n-grams. So 3-gram is a 3-word sequence of words like please turn your homework. And we'll see how to use n-gram models to estimate the probability of the last word of an n-gram given the previous words, and also to assign probabilities to entire sequences. And for example, unigram, this is just unigram. Bigram, it's binary. You see, trigram, you have 3 words in a sequence. So n-grams and transformers. So although n-gram language models have been outperformed by the state-of-the-art neural language models, they are still, as I said at the beginning of this lecture, they are still widely used, especially in speech recognition, due to its high efficiency in inference. So this is an interesting article in 2019, and also n-grammer, augmenting transformers with latent n-grams. So one way to estimate the probability is from relative frequency counts. We take a very large corpus, count the number of times we see, for example, its water is so transparent that, given on this, what is the probability of V? So we count this, we count overall all of that, and we divide it by the counts of the subpart of that, which is its water is so transparent that. So there is included in the denominator. So in this way, we can calculate the probability of there given this sentence. So you may say, how can we calculate this? But we use chain rule, and so the probability can be decomposed to probability of x1, probability x2 conditioned on the previous one, probability x3 conditioned on previous two words, and so on. Models that assign probabilities to sequence of words are called language models. So anytime that you're calculating a probability of a sequence, it's a language model. You're creating a language model, right, with different tools. So how can we compute the probabilities of entire sequences? So one thing we can do is decompose it using the chain rule, as I said. So using the chain rule, we can decompose it very beautifully like this. And by this, this terminology means 1 to till k minus 1. We use it in everywhere. And we apply the chain rule to words. So for example, what is the probability of this word from W1, W2, Wn? Then we can calculate it like this. But we approximate the reality because it's very hard to compute this, so we approximate it. I mean, instead of conditioning on W1 till Wn minus 1, we just use the Markov assumption. We say that it's just enough if we know Wn minus 1, so it's conditionally independent of anything else. And this is our Markov assumption, and we approximate the reality. So instead of this part, we just say it's enough to condition on the last previous word. So if we combine this and substitute that, you will notice that everything becomes very simplified. So it's like abstract art minimalism when you go to lower and lower n-grams. But when you go to hyperrealism, hyperreal art, which I don't like, it goes many higher order grams. So n-grams, n goes to very large. But I like minimalism, abstract art, because you can, first of all, you can do it very quickly. Second of all, you don't need, because if you go in this direction, it's just photography. But if you go in this direction, it becomes art and meaning and life and woman and freedom. And so this is abstract art. You approximate the reality. But this is the realism, although it is not hyperreal. Hyperreal is just business. I don't see any art in hyperreal. It's just photography. Call it photography. Why do you call it art? So. So we approximate the reality. Instead of conditioning to all the previous words, we condition to the just one word. And for bigram, it becomes this. So maximum likelihood estimation is our friend. You will see that everything will be reduced to this after solving an optimization problem. So it's just counting. Everything is reduced to counting. Counting Wn minus 1 Wn divided by Wn minus 1. So maximum likelihood estimation is our friend. So for this example, I am Sam. You will see how we can easily, quickly calculate this because it's just counting. And to prove that it is just counting, I just like the Lagrangian multiplier. So you have some constraints, and so you want to maximize this log likelihood. And if you find the derivative, take the derivative of this Lagrangian with respect to the parameters that we have, you will notice that finally your solution is just what I've just said. What is intuitive, of course, because you're counting that again. So next time you want to use n-grams, just use counting, because we already know that this is the proof. And evaluating language models, there are two methods. Extrinsic, just embedded in an application and measure how much the application improves. And the other approach is intrinsic. An intrinsic evaluation metric is one that measures the quality of a model independent of any application. Whichever model assigns a higher probability to the test set, meaning it more accurately predicts the test set. So given two probabilistic models, the better model is the one that has a tighter fit to test data, or that better predicts the data of test data, and hence will assign a higher probability to the test data. So our measure when we talk about language models is just perplexity. It means the desire that, for example, we cannot guess it. So we want, this is our perplexity. The perplexity is the inverse probability of test set. And so we can expand the probability like this. And this is a measure you see in many papers. They use perplexity when you're talking about language models, if it is good or bad, if it is trained well or not. In the world of transformers, in the world of, if you are using any kind of self-attention, perplexity is your friend, because it is the measure of measuring if this language model is working properly or not. And the perplexity of a bigram language model is as simple as this. It's inverse of probability of your word given your previous word. So you see, if your probability of your word given your previous word is high, it means that it has lower perplexity. So in contrast to accuracy, perplexity, lower is better. But in accuracy, higher is better. But perplexity, lower is better. It means that we are less surprised. Already the model can capture it. Our training was well, so we can capture all these combinations. And for example, the perplexity of unigram is too high. When you go to bigram and trigram, they become less and less, because we are less surprised. For example, when it go n-gram, we have almost got it, because it should be a very small number. Because we are less surprised if we have lots of words, then we can estimate the next word. But if we have just, for example, 3 words or 2 words, this word, if conditioned on this word can be anything. So we are very surprised. The perplexity will go high. Oh, it's at the end of the lecture.